All right, let's go ahead and put away the inverted lecture for now. So last time we were talking about radical reactions, and as you all recall, especially since you just worked problem 1, there are 3 steps in every free radical reaction, right? And they are initiation. Man, I love it. That's great. Nothing got lost over Thanksgiving. Great. All right. So we've got initiation, propagation, and termination. And those steps, can you tell me what the free radical concentration is at any given moment during the propagation stages? It's essentially 0. That's right, because a radical is very reactive, right? It will react with just about anything that it can, including oxygen, to get its octet, right? And so radicals are very reactive. However, not all radicals are equal. And that's what we're going to talk about today. If you look at the free radical chlorination reaction, what you notice here is that the energy of activation is pretty low. About 16 kilojoules per mole is the energy of activation for a chlorine radical to abstract a hydrogen atom and generate a carbon-centered radical. That energy of activation is actually quite low. So what does that tell us in terms of the reactivity of the chlorine radical? It reacts with just about anything that it can, right? Right? So would you expect that to be a selective reaction or an unselective reaction? It's very unselective. So if you have a molecule that has primary hydrogens, secondary hydrogens, and tertiary hydrogens, the chlorine radical will react with all of those. Now you will get some selectivity, but it's very minor. Is that practical on a laboratory scale? No. However, if you look at bromination, what can you tell me about the energy of activation? Much higher, right? And if you look at that, 16 kilojoules per mole versus 74 kilojoules per mole, that's quite a bit, or 78 kilojoules per mole, excuse me, in the energy of activation. That's substantially higher. So will a bromine radical just react with anything? No, it will only react with the most reactive hydrogens, which are which hydrogens? Primary, secondary, tertiary. Okay, Yusuf, you're right. Why is it the tertiary hydrogen's more reactive? That's exactly right. That tertiary carbon-hydrogen bond is weaker than a primary carbon-hydrogen bond, okay? And so bromination actually goes after the most reactive hydrogens in a very selective manner, okay? Brominations actually are practical on a laboratory scale. We do free radical brominations all the time. They like to react with allylic hydrogens, benzylic hydrogens, like on toluene, which is one of the problems on the inverted lecture, okay? But in terms of reacting with primary hydrogens and secondary hydrogens, they'll only react with them if they're available, okay? And so, for example, we can do this reaction with methane because that's the only hydrogen available, but the energy of activation is actually quite large. So brominations, the take-home message from this slide is that brominations are actually selective. You will typically get reactions with the tertiary hydrogens, and it's usually quite selective, okay? Whereas chlorinations, you usually end up with a mixture of products, okay? So this is what you can see in terms of the reactivity of halogens and free radical reactions with methane. Fluorine should actually have another little alligator or two there because it's extremely reactive, okay? In fact, so reactive that it goes boom. Really, chlorinations and brominations are what we're dealing with. Iodinations, really no reaction, okay? And we've seen this before. Iodine doesn't like to add to double bonds, and it doesn't like to do free radical chemistry with hydrocarbons either. Whereas bromine and chlorine do this quite well. Fluorine, you mix it together, yeah, it'll react, and it'll also blow up your vessel. So it's a little bit of a problem. Now, if you look at the energetics, I do not expect you to memorize this. You all did this in general chemistry, okay? This will not be on the exam. But the take-home message here is that if you look at the energetics, okay, of the overall reaction and you add things up, you can see why certain reactions are very exothermic and others are not so ready to go. So if you look at the initiation stage, right, it looks like we should be able to initiate a free radical iodination a lot easier than any of these others, and in fact that's true. but that's not the only step. If you look at the abstraction of the hydrogen atom, you can see that chlorine and bromine, right? This is fairly low. That's very exothermic, right? That, again, you can see why boom. But you can see that that's a fairly high value here for iodine. And then in the last step where the chlorine radical, last propagation step anyway, where the chlorine or the carbon radical reacts with the halogen, you can see what's going on there as well. Okay, so very negative, okay? And this is the more positive, if you will, on that line. And so you can see why iodine is very unreactive. Chlorine and bromine are really practical, and fluorine you can see why it's not practical at all. It's too energetic, okay? So now if we look at the chlorination of propane, propane has 3 carbons and 8 hydrogens, right? And what kind of hydrogens does propane have? Primary and secondary, right? And so if we look at the reaction of propane with chlorine, so if you came into the laboratory, you took a vial of propane, you mixed in some chlorine, and you shine a bright light on it for a while, you're going to get 1 chloropropane in about 45% yield, and you're going to get 2 chloropropane in about 55% yield. For all practical purposes, that is some selectivity, but it ain't much, right? 45 to 55, if you use government numbers, that's 1-to-1, right? Pretty close to 1-to-1. Pretty impractical, okay? So how would you determine these ratios? How would we determine these ratios in the laboratory? What technique do we have that we can use? You could use NMR, right? These molecules would actually have different, ooh, that's bad. That's wrong. That should just be CH. No 2 there. Make sure you mark that. This book has had a lot of errors with their slides. So there is no 5-bonded carbon, okay? Keep that in mind. So yeah, we could use NMR, and we could integrate the hydrogens, right, and determine the ratio. What other technique have you all used that could readily determine these? Kind of a box with an oven. Ah, there you go, GC. GC works really well for these types of molecules because they're low molecular weight. They boil pretty easily. You could inject them into the GC, and you would see that the peak would be about 45% this and about 55% that if you looked at the 2 peaks, okay? Now, we can use this information to determine the relative reactivity of a primary hydrogen versus a secondary hydrogen in a chlorination reaction. Because we know that the statistical factor is 3-to-1. If the radical reacted just based on statistics, you would expect to have 3 times as much 1 chloropropane as 2 chloropropane because there are 6 primary hydrogens and only 2 secondary hydrogens. So at random, that's a 3-to-1 ratio, right? But this isn't random, okay? But that's the statistical factor, okay? And so now we can actually calculate what we call the intrinsic reactivities in this particular reaction. That is the quantity of 1 chloropropane to 2 chloropropane, okay? And so now we can calculate. So let's see how we do, and this is as difficult as the math gets in organic chemistry, by the way, okay? So we have our data. You did this in the laboratory, and again, that's not a 2, okay? And what we actually see is that the statistical, or excuse me, the intrinsic reactivity, the secondary hydrogens are almost 4 times more reactive than the primary hydrogens, okay? How did we calculate that? Well, we know what the product mixture is. We know that 2 chloropropane divided by 1 chloropropane is 55 to 45, okay? Now notice I put the one that's in greatest abundance on the top just so I can deal with whole numbers as opposed to things less than 1, okay? And that's going to be equal to the statistical factor times the reactivity of a secondary hydrogen over the reactivity of a primary hydrogen, okay? Notice 1 chloropropane, its quantity, the statistical factor, and the relative reactivity, okay? So that's how because this arises because of an abstraction of a primary hydrogen. That's why you have the reactivity of the primary hydrogen down here, okay? So now we know what that is. We know that the statistical factor is 1 to 3 because there's a relative ratio of 1 to 3, right? So we've got that set up. Now how do we calculate this? We just do a little algebra, right? And we end up with 3.6 to 1. This will be on exam 3. Okay, you will have to do a calculation like this. Does that mean that all secondary hydrogens are 3.6 times more reactive in all reactions? No. This is in the chlorination reaction. So if we did this for bromine, the number would actually be different because it depends on the reactivity of the radical. Okay? But what you can tell from this is that on, roughly speaking, a secondary hydrogen is 4 times more reactive than a primary hydrogen in a free radical chlorination. And that's why we don't get a 3-to-1 ratio of products, okay? Because the hydrogens here are a lot more reactive. They're going to react more frequently, and that's why you see a relative abundance of 2-chloropropane over the 1-chloropropane, okay? Now let's look at the chlorination of isobutane. So here we have isobutane. We're going to chlorinate it, and we get this ratio of isobutyl chloride being 63% of the mixture and tert butyl chloride being 37% of the mixture. Before I go forward, real quickly on your own paper, calculate what the reactivity must be of a primary versus a tertiary hydrogen. You've got all the data you need to give me the relative reactivities. What's the statistical factor? It is 9 to 1. I've got 9 primary hydrogens for every single tertiary hydrogen here, right? So let's walk through the calculation. I know my ratio, 63 to 37. Right? My statistical factor is 9 to 1. And so I'm going to put, or they put, the tert butyl chloride on the top, isobutyl chloride on the bottom. They know that that's a 37 to 63 ratio. The statistical factor and the reactivity of the tertiary to the primary. Okay? And so when you set this up, you can do the algebraic manipulation, and you can see that it's a 5.3 to 1. Okay, so a tertiary hydrogen in a chlorination reaction is about 5 times more reactive than a primary hydrogen. Okay? Now, it doesn't matter which one you put on top and which one you put on bottom, as long as you're consistent. So tert butyl chloride, its yield and its reactivity. Okay? And then, of course, its number and the statistical factor all have to be on the top. And then for the isobutyl chloride, same thing on the bottom, and you'll be okay. Just pay attention on the exam to how I ask it. So if I say the reactivity of the tertiary to the primary, you have to set it up like this. If I say the primary to the tertiary, you would invert it. Okay? So always pay attention on the problems, know what it's actually being asked. Okay? Now, bromination, a little different. Here we have isobutane, bromine, shine a bright light on it, and what we get is pretty much so all tert butyl bromide. You only end up with a trace of isobutyl bromide. So how can we make, what kind of assumption can we make in terms of doing a calculation here? It's going to be a really high ratio. So immediately, right, you can eliminate things that aren't very high in terms of a multiple choice exam. Right? Things that are like 1 to 1, 5 to 1, that's not really high, right? Now, what we can do is we can also make an assumption about what a trace is. This says greater than 99%, okay? Now, what we do to give a conservative estimate here is say it's 99 to 1. That's going to overestimate the reactivity of the primaries, obviously, right? But it's going to give us a ballpark figure. And so when we do that math, tert-butyl bromide, isobutyl bromide, the statistical factor, or the ratio 99:1, excuse me, the statistical factor and the reactivity. We know it's a 1:9 ratio. We do the math. We get about 900:1 reactivity difference, okay? That's vastly different than what we saw with the chlorination, right? What did we see in the chlorination? About 9:1, right? Or something like that. No, it was 5:1, right? So 5.3, right? Or something like that. So big difference. And you can see that the reactivity of these hydrogens depends on what radical is doing the chemistry, okay? And so that tells us that, you know, if we're being conservative here by calling this trace being 1%, really this is probably greater than 1,000:1, right? But, you know, how do you quantify a trace? Give it 1% and see how it goes, okay? And again, this is a very low estimate. Now, radical reactions can occur such that you generate chiral centers. So for example, if we take pentane and we chlorinate it, what kinds of hydrogens do we have here? We have primary and several secondaries, right? Are all the secondaries identical in terms of the products that we would get? No. The primaries are, if we abstract a hydrogen and replace it with a chlorine here, we'd end up with 1 chloropentane, right? But what about if we replaced one of these hydrogens with a chlorine? What would we end up with? 2, and if we abstracted this one? And this one? There you go. That's right. So we have a possibility of how many products? 3, right? So if we get 1 chloropentane, we get an achiral product. If we get 3 chloropentane, we end up with an achiral product because there's no chiral center. However, if we abstract one of these hydrogens and replace it with a chlorine, we end up with 2 chloropentane, which is chiral, right? It has a chiral center. There are 4 different things around this carbon, right? There's a propyl group, a methyl group, a hydrogen, and a chlorine. So that's 4 different things around that carbon. Will we get the R enantiomer, the S enantiomer, or a racemic mixture? It will be racemic. And how do you know that? Okay, very good. That's right. Yeah, so we're going to get a racemic 2-chloropentane out of this. So totally, how many products are we really getting? We're getting 4, right? You're getting the 2 achiral materials, and then you're getting 2 enantiomers of 2-chloropentane. One being R, the other being S, and you're getting those in a 50-50 mix. So a lot of products out of this particular reaction. And we know that the selectivity of the chlorine radical is very unselective, so we might expect to get, you know, I wouldn't say equal, but substantial amounts of all the products, right? So not going to be quite equal, but it's going to be a substantial amount of all of them. Definitely not going to be traces. So let's think about the reaction pathway, okay? And let's ignore the initiation and the termination steps. Let's just focus on the propagation steps here. So we've just initiated, we've got chlorine radicals, and now the chlorine radical can abstract a hydrogen atom from the secondary, one of the secondary carbons, and in this case, carbon number 2, right? It can either remove the one coming out of the plane or the one going behind the plane, it doesn't matter. We end up with a trigonal planar radical. Okay, so we have, what's the hybridization of this? It's sp2, right? And it is planar. And so now this radical is going to react with chlorine, which can either react from the top face or the bottom face, and in doing so, we end up with a mixture of enantiomers. And if you look at this, since this is planar, the odds of attack of the radical from the top or the bottom is exactly 50-50. There's no preference, okay? And so you end up with a racemic mixture. Notice that this orbital, we draw the electron in the top, but really that electron is in the entire orbital, okay? Some people get confused and think, well, the radical's on the top, so it should give you more of that product. No, the radical's in the entire orbital. It's just you put the dot somewhere, right? You could have put it at the bottom. It would have been okay. You just can't have 2 dots, okay? And so we end up with a racemic product. Now, if you started off with a very expensive starting material like S2-chloropentane, so you made 2-chloropentane and you isolated one of the enantiomers, now you can do a free radical reaction where you can generate 2 chiral centers. And in generating two chiral centers, do we have to generate them in equal amounts? No, okay? Because they're diastereomeric transition states. And so the same thing happens. The chlorine radical will extract one of these hydrogens. You end up with a planar sp2 hybridized carbon-centered radical. But is the top now equivalent to the bottom? Why not? That's right. The chlorine's on one face and the hydrogen's on the other. That's clearly different, right? So the odds of attack from the top or the bottom do not have to be equal. And so attack from one face would give me the 2s, 3s, 2,3-dichloropentane, and attack from the other face would give me the 2s, 3r, 2,3-dichloropentane. And these are enantiomers of one another or diastereomers? Diastereomers. And do diastereomers have to have equal ratios out of these types of reactions? No. And so you might expect to get one of these products in higher yield than the other. Now, I will tell you that in this particular reaction, the amount that you get is nearly equal. But you might expect, for example, that maybe this one would be the slightly larger amount. And why might I predict that? That's right. So chlorines will kind of repel because they got lone pairs of electrons, and so you might expect that they might want to be on opposite sides of the plane that we have here in this free radical intermediate. Okay? So we would not expect to get these in equal amounts. So anytime you start off with a chiral center and you generate a new chiral center, you don't have to get it in equal quantities. Okay? Now, if we look at the reaction of alkenes with free radicals, we have some interesting chemistry to talk about as well. So if we look at our alkene that we have here, we know that we can add HX across the double bond, right? So if we take this alkene and we react it with HBr, we would expect to get 2-bromopropane, right? That follows whose rule? Markovnikov's rule, right? The hydrogen goes to the carbon with the most hydrogens, the bromine goes to the other carbon, excuse me, and you end up with 2-bromopropane. Okay? It goes through what kind of intermediate? That's a carbocation reaction, and that's just the addition of HX across a carbon-carbon double bond using a double-headed arrow to show the reaction mechanism. However, this happens only when you have HBr in the dark. If I was to do this outside on a nice, bright, sunny day in the sun, you would actually end up getting 1-bromopropane, the anti-Markovnikov addition of HBr across the carbon-carbon double bond. Okay? And you end up with 1-bromopropane. The fact that I have to have strong light to do this tells me that this is a free radical reaction. Okay? Another thing that you need to know is that this only happens with HBr. HCl does not do this. Why would HBr undergo this free radical reaction whereas HCl does not? In this case, HCl can only add to the carbon-carbon double bond. Yeah, that won't happen, though, with HCl. You'll only get the Markovnikov addition with HCl. You won't get any anti-Markovnikov addition, even if you shine a bright light on it. Which tells us what? Well, it is selective under certain conditions. That's a true statement, but it doesn't explain the observation. If I shine a bright light and I still get Markovnikov addition with HCl, it's not radical. That's exactly right. Why isn't it radical? Is the chlorine radical stable or unstable? It's unstable relative to the bromine radical. That's right. And so it has to do with radical stability. Okay? So HBr has this ability to add in both a Markovnikov and an anti-Markovnikov reaction because it can either do chemistry that is heterolytic or homolytic. Okay? And we can do that chemistry fairly easily. Okay? So we'll have a little problem on the mechanism here in just a moment. But I want to go ahead and move on and talk a little bit about this idea of why free radical chemistry is important. And this was a diagram that I showed you at the very beginning of this chapter, right? And I showed you that arachidonic acid, which is something that just about every biological organism that I know of has in abundance, these things undergo free radical reaction to make these things called prostaglandins. And prostaglandins, as you'll recall, are responsible for a variety of things. Anybody remember any of them? Pain, fever, inflammation, arthritis, you name it, right? And we talked about a way in which we could block that so-called COX-1 enzyme from forming these by using something like ibuprofen, right? It sits in the active site and blocks the chemistry from happening, okay? But there are other things that we need in our diet that help with this type of problem. Once you generate the radical, you've got a problem, right? Once you generate the radical, ibuprofen doesn't help you. Ibuprofen tries to prevent this from happening by blocking the enzyme. But this can actually happen in the absence of enzymes. This can happen under just oxygenated blood. And so generating a carbon radical will continue to react with oxygen and form prostaglandins. Does anybody know what types of molecules you need to have in your diet that prevent this type of chemistry from occurring? Antioxidants, that's exactly right. Okay? And so an antioxidant technically should be called a chain-breaking antioxidant. Okay? Once you generate a radical, it will react and it will continue to propagate, right? Antioxidants don't stop radicals from forming. They break that propagation step. Okay? They help terminate the process, if you will. Okay? Although they're not terminators in the strict sense. And so antioxidants, also known as anti-aging things, et cetera, et cetera. So you see all these commercials about these anti-aging creams, and what do they almost always say that they contain? Antioxidants, and usually they say they contain vitamin E. Okay? Now, vitamin E is a natural antioxidant. It's a very potent antioxidant. We get it in our diet. We need to have so much of it. Okay? What can you tell me about this molecule? It's got a few chiral centers. We got one here, and one here. Okay, so it is a chiral molecule. What else can you tell me about it? What's its functional groups? Okay, it's got a phenol. Well, that OH is a phenol, yeah. So it is an alcohol, but it's attached to an aromatic ring, so it's a phenol. And we've got an ether, right? And we've got a bunch of hydrocarbon, right? So is this going to be dissolved in your water or in your membranes? In the membranes. And vitamin E is actually responsible for your cell membranes from oxidizing and breaking down. I mean, it helps prevent that from happening, okay? And so vitamin E is a nice antioxidant. There is a synthetic version of it called BHT. How is BHT similar to vitamin E? It has a phenol, and it also has some hydrocarbon. It's a lot simpler in the sense that it doesn't have chiral centers, okay? Now, for those of you like me who like to eat packaged and prepared foods, okay, they don't supplement that stuff with vitamin E. It's too expensive. They use the synthetic BHT. So if you like things like Vienna sausages, which isn't a sausage but still tastes good, right? Pork sausage, whatever the case may be, usually to keep that stuff from going bad, spoiling, because it's got a lot of fat in it, right? To keep it from spoiling, they add BHT, which is a synthetic antioxidant, and it's known as butylated hydroxytoluene. But the business end of it, the phenol, is exactly the same as the business end of vitamin E. Okay, and so the chemistry that these two do is actually similar, especially for something like a packaged meat product. Okay, the chemistry of BHT in the body would be slightly different because it wouldn't pack nicely into a membrane, but nobody really cares about that. The sausage people just want to make sure that your sausage makes it to your grill without being rancid. Okay, so antioxidants are responsible for this. And so what happens is, once you generate a carbon-centered radical, okay, so if you can think of this as being that arachidonic acid, for example, okay, that carbon-centered radical is very reactive. Why? It wants another electron. That's right. Where can it get it? It can get it from the phenol. And so it will react using these single-headed arrows, if you will, to get a hydrogen atom. So we reduce the radical to an alkane, basically. And in doing so, we generate an oxygen-centered radical that is a phenol radical, or a phenoxyl radical, okay? This radical is actually quite stable. Are stable things more reactive or less reactive? Less reactive. So you're taking a very reactive radical, which will age you, and you're generating a less reactive radical, which your body can deal with. Kind of nice. This radical is so much more stable because of all the resonance structures we can draw for it. So it doesn't like to go and react with your membranes and pull hydrogens off of them and destroy them, okay? In fact, vitamin E is not the only antioxidant you need in your diet. Does anybody know what the other one is? Not vitamin K. Vitamin C. Vitamin C is an aqueous soluble antioxidant, whereas vitamin E is what? It's fat soluble, right? And so once you generate this radical, it wants to get reduced as well. And it gets reduced by vitamin C, which is in the aqueous part of your blood, okay? And you oxidize vitamin C, and then you basically can urinate out the byproduct from that, okay? So it's a whole antioxidant cycle, and it's really complicated, but we're just kind of covering it. It turns out that if you have too much vitamin E and not enough vitamin C, it's actually hazardous to your health. Okay? So that's why some people will tell you to take large quantities of vitamin C in your diet. I'm not giving you that advice, but there was a guy who won a Nobel Prize who took several grams of vitamin C every day and lived to be in his 90s. Anybody know who that was? He won 2 Nobel Prizes, one for chemistry and one for peace. Does that help? Huh? No? Yes, but no? There was. His name was Linus Pauling. Okay? So he won 2 Nobel Prizes, but every day he took at least 2 or 3 grams of vitamin C in his diet. Actually weighed it out and mixed it in a drink or whatever and took it. Yep. Now some other things that we can do with free radical reactions, okay, are polymerizations. So for those of you in the polymer science department, you know that polymers are these large molecules made up of smaller molecules called monomers, right? And a lot of this can actually be done through free radical chemistry. I should mention here that not all polymerizations occur by free radical chemistry, so I don't want you to leave with that impression. But free radical chemistry is a significant chunk of what's going on in polymerization. So for example, if you take ethylene, you can polymerize it into polyethylene. Does anybody know what polyethylene is useful for? Water bottles. What else? I don't know if it's used, polyester is, but I don't know if polyethylene is used in clothes. Just plastics, okay? Turns out, just a little history lesson, back in the 70s, 80s, most gas tanks were made out of metal. In your car, you had a crash, metal punctures that leaks out, right? And if there's a spark, there's a flame, there's a fire. What do we have now? Polyethylene. Polyethylene is tough. It can be collapsed and crushed without being punctured, right? And it's made by this polymerization reaction of ethylene monomers coming together to form polyethylene. So free radical chemistry to the rescue. No more car fires due to punctured and ruptured gas tanks. There are other useful polymers that come from this. So you can take vinyl chloride and make PVC, sewer pipes, water pipes. You can take propane and polymerize it to polypropylene. This is AstroTurf. Okay, so if you ever go out on the field, on the AstroTurf, you're walking on polypropylene. If you like to drink hot coffee and keep it hot, you use styrene products. Polystyrene, which comes from the polymerization of that particular polymer. Okay? So if we look at radical polymerization, we still have the same 3 steps. We have initiation, we have propagation, and we have termination. So usually when you do a polymerization of a monomer, usually you use something like a peroxide type initiator because we know the oxygen-oxygen bond is fairly weak. You heat it up just a little bit, it decomposes into alkoxy radicals, which will react with the carbon-carbon double bond to generate a carbon-centered radical. That carbon-centered radical then enters into the propagation steps where A radical reacts to get another radical, and this will continue on over and over again to give us higher and higher molecular weight polymers. So your molecular weight comes largely from the propagation steps. Now once our monomer starts to run out, now we have an excess of radicals and they come together and combine and form no radicals, right? So we have these initiation, propagation, and termination steps. But most of what the polymer people are really interested in is continuing in a controlled fashion those propagation steps relative to initiation and termination to control molecular weight. And that's very, very important, right? Because molecular weight determines the properties of your polymer. Low molecular weight polymers are usually liquids or gels or gooey gunk, right? Stuff that we generate by accident in the lab usually. Higher molecular weight polymers are usually more solid. They can be more crystalline. They can be tougher. They can put all kinds of properties into them, etc. All right, we'll continue with this on Wednesday. Bring your inverted lecture with you on Wednesday. We'll work on it in class, and we'll go from there.
What will we do in class?
Huh?
What will we do in class?
I doubt it.